So as technology accelerates, like right now we're recording on three iPhones, right? As things get smaller and more advanced,
Yeah.
does the science and research start?
Oh.
Yeah.
Oh, absolutely. Oh my goodness. I just had this conversation with my students in group meeting yesterday. So we're working with a very small scale model of a supernova event. Here's what I mean by that. A real supernova probably gives off on the order of 10 to the 58 neutrinos. That's a 10 with 58 zeros after it.
Oh.
Our model, and you may ask why bother, but our model uses many, many fewer than that. We are actually right now focusing on the interaction of just two beams of neutrino.
Two out of like the 58.
Well, it's not that silly. It's two beams of, let's just say, a ridiculously small number compared to 10 to the 58.
Okay.
But it's useful. It's a useful step. Science is a series of little itty-bitty baby steps.
More than nothing.
It's more
something.
than nothing.
Yeah.
But what we're doing now is this year, what we're looking forward to doing is working in conjunction with people who model larger scale simulations.
Okay.
And what we're still going to hit up against is computational limitations. So we are looking at just a handful of neutrinos because we would like to get a handle on that physics before ramping it up to more and more. But at a certain point, we're going to be limited not because of the question we want to ask, but because of the computational expense of being able to do that.
Okay.
So one of my colleagues here works on quantum computing. Yeah. And given what's happened with AI over just the past handful of years, and ChatGPT, my God, what are we going to see emerge and how quickly? And I don't know, that's not my field. I can introduce you to my colleague I'm talking about if you're interested. So, and I don't know how to predict that. I don't know how to predict how much we're going to be able to do. Are we going to be able to simulate a 10 to the 58 neutrino event in my lifetime? I really don't know. I'm not in that line of work, but I'm very curious and excited to see how quickly this accelerates.
So what
I mean by that is how quickly the rate at which computations get easier and easier and easier accelerates. I mean, one of my former mentors will say, do you know how big the computer was that I had when I was your age? You carry that thing around in your backpack like it's nothing. So I couldn't have picked that thing up.
Every time I open up my laptop,
smaller.
I take a moment and I'm just like, I'm so grateful that this machine exists in my lifetime. This is so wonderfully amazing. So what do you think that means to like the human story? It's just so phenomenal. Can we solve things like electricity? Or
can we solve,
like energy on Earth, or
you mean not being so reliant on these sources we're using now?
Yeah, like through learning, taking astrophysics and other realms of science and merging it with the technology.
Well, sure, we've already got solar energy. So I'm a little nervous at answering the question because this is not my area of specialization. But we've got solar energy and we've got hybrid cars now. I don't know how quickly that's going to start replacing. I was making a joke the other day. Oh yes, I had forgotten my power cord, and my laptop was on its last legs. 10 more minutes left before it died. And so what is that going to look like in 10 years? I really can't tell you. But astronomy and astrophysics has led to our being able to understand how to harness energy from the sun.
Yeah.
And that's already here. That's been here for what? I'm betraying my ignorance now, maybe 20 years?
You're asking the wrong person. So what are some of the uses from some of the everyday uses that have come from studying astrophysics?
Everyday uses. Well, okay, here's one example. let me lump all these things together. There's a way of, let me just say physics. There's a way of training your brain to think about how dynamical systems work. And that in more recent decades, there's a way of figuring out how to translate that into a computing code so that you can get computers to perform tasks that, you know, it would take you 100 years to do, that translate to other areas. So for example, one of my very first undergraduate students, I met him through a class. He was the best in the class, so I approached him and said, do you have any interest in research? And he said, oh, yes, but don't you do astrophysics? Kind of like cringing. And I said, yes. And he said, I have to be honest with you. I couldn't care less about astrophysics, but I've heard that you use the supercomputing cluster here. And we do. And I said, yes. And he said, well, what I'd really like to be able to do is I want to go into to neuroscience, into neural prosthetics. And it was interesting because I actually did a postdoc in neuroscience before I started my astro research. And my point is going to be that skills translate. So he said, so what I'd like is to join your group, so long as you don't expect me to learn anything about astrophysics. I really want to learn how to control the supercomputing cluster. I want to learn how to build my own someday, and I want to learn machine learning. I said, great, you're in. And oh, God bless him. He set the whole supercomputing cluster up, you know, our interaction with it. I still don't know how it works because I, like the science questions, I want to give that to the students. So it was just a perfect, it was a perfect relationship. So he got that all up and running, and he's an expert on it now. He's graduated. I have to email him sometimes with questions about how it works because I still haven't bothered to learn. I'm a little bit lazy in that way. So my point is, you can harness the skills from this discipline and take them in many, many new directions. So that's one possible answer to your question. Yeah. But there's, go ahead.
Elaborate on supercomputer cluster.
Oh, sorry. Let's go back to computational expense. It takes time for a computer to do a job that you tell it to do. So you have a calculator built into your laptop. Okay, so you type in, you bring up your calculator and you type in 2074 divided by 17.6, because you probably don't want to do that in your head. Yeah. And you press enter, and it gives you a result pretty much instantly as far as you're concerned. Right. But these codes, these simulations we do, are much, much more computationally expensive. Okay, so hundreds, maybe thousands of lines of code. That takes time for a computer to run. And how much time depends on how much you've got on your machine. So if I wanted to run these simulations on my laptop, we wouldn't be publishing a paper anytime soon. It would take years. The supercomputer is much larger. We run it remotely. So it's got much, much more power. It runs these simulations much faster. And we control it locally from our computers. But we had to set up the means of communication between our computers and the supercomputing.
So the supercomputer, is that a quantum computer?
No, that gets back to another topic we began. Oh, someday. So that's what I meant when I said, where are we going with this? Because to date, our supercomputing cluster, it's very impressive in what it can do, but we can't run a simulation with 10 to the 58 neutrinos. That would crash it. It would take, my students would graduate before we were finished. I am very curious to know how the quantum computing front will develop, because we would love to be able to multiply the efficiency of that cluster by a factor of 1,000, 10,000.